that our government of India has announced the National Cybersecurity Awareness Month this October 2021. So under this awareness program, we, the CSE Department of IIT Kharagpur, we have planned to conduct a distinguished lecture series on cybersecurity year-wise, that is a monthly one, and the speakers will be from reputed, they are from reputed researchers, from academics as well as industry. So today we have Professor Aniket with us, and he is an eminent researcher in applied cryptography, all of we know, and in particular the cyber security and privacy. So he's an associate professor in the Department of Computer Science, Purdue University, USA. First of all, I thank you, Professor Kate, for accepting our invitation with this short notice, and I welcome you as the inaugural speaker of this session, and we hope that obviously it will be a nice thing, and we will enjoy this lecture. Okay. So I hand over the things to Professor Kate. So please do that thing. Thank you. Thank you.
Yeah. Hello, everybody. Thanks a lot for the invitation. It's always nice to have opportunity to talk to students and faculty members at IITs for the topics that I work on. And indeed, I look forward to hear your thoughts and comments as I present some of the things that I have been working on in the metadata privacy space. And this talk will include construction analysis as well as some kind of a lower bound results. Brief introduction for myself. I work on, as I can call as people-centric privacy and security problems using cryptography and distributed systems. These days, indeed, my focus has been on cryptocurrencies and blockchain technologies, as well as I have continued to work on privacy and accountability for publishing and as well as retrieving information. And recently, I have been focusing on the deleting information, where I've been actively working with Professor Moinak Mandal. My research typically involves using cryptography, distributed systems aspect, and like many of us, it has become quite a lot of data-driven in last several years. So topic of our discussion today will be communication privacy, where when we talk about communication privacy, there are interesting different aspects that has to be considered. And the key question that one asks for communication privacy is who is talking to whom and what are they talking about. In this particular case, the what aspect is certainly one of the prominent aspects which we deal with SSL and TLS protocols, which stand for secure socket layer and transport layer security protocols, which are we can call it the de facto standard for the internet security today, which allows us to have end-to-end secure communication, even in presence of a network adversary who can possibly completely control the network. They can always stop the communication, but they cannot modify it without getting detected, or they cannot even read it without getting detected. And that's the aspects where the communication data get private using such mechanisms. And whenever you visit any website with HTTPS, in fact, you are sure that some intermediary is not cannot actually determine the content of your communication to some extent. I mean, certainly there's still attacks that happen in this environment, but that certainly is the case in most cases that we get privacy for our communicated data. However, the focus that we have today is more not to do with the data, but more with the metadata. Even when we use something like SSL and TLS, it's still possible for anybody to figure out which source IP address is sending packets or information to which destination IP address. They can also link multiple communication that are happening between two entities and create linkage between them. So that's where unlinkability comes in picture. And they can also figure out access privacy, like what is the pattern that is employed by when you are accessing, let's say, a database, and in how entries are accessed can be also find out. And these teams, and there could be indeed more that can be added to these, can be put in the bucket called metadata. And indeed, it has been extensively employed in both state as well as the organizational state to figure out information about the users and possibly basically go after user based on this metadata is certainly something which is prominent. And our talk today focuses on what kind of techniques we can employ towards providing some privacy protection for such metadata. So, in particular, when we look at the problem that we'll be focusing, even in this meta-beta space, is could be called as communication anonymity. So, what is anonymity when we talk about in the context of networks or internet? It can be called as the state of being not identifiable within a set of individuals or subjects. And unlike other aspects of privacy in general, this is exclusively individuals or subjects' property. And essentially, if you are the only one who could have done that action, then anonymity is conceptually broken. And that's the reason anonymity loves company. There should be others who are trying to do the similar actions or save or trying to visit same website or trying to follow the similar patterns. That is essential to get any kind of anonymity in such an environment. So when we look at anonymous communication network, as I already mentioned, if you look at a packet and just based on that, you can determine who is sending information to whom. And that could be sufficient to figure out or break the anonymity in general. So that's the reason, essentially, to get anonymity, it may involve that your packet now does not directly reach from sender to the destination, but it may take some route which involve multiple participants or multiple overlay nodes on the way. And your hope is that while that is happening, other packets from other people also get mixed or get shuffled with your packets, and that can provide you anonymity. We are going to look into the more detail how that may happen, but that's the core idea, that somehow there should be an opportunity for packets, network level packets from different entities to get mixed while it is still getting transferred on the internet. But as you can see, that certainly is not sufficient, because if they can see the contents of the packets and they remain exactly the same, then that could be traced as well. And that's where the cryptographic techniques are also necessary, that even those packets are flowing in different parts of the network, that they get updated and modified so that adversary who is sitting at the, let's say, an autonomous server level or AS level, can just look at the packet in different part and figure out, oh, this is the same packet, and I know who is the sender and who is the receiver. There are certainly, when we look at any kind of anonymity solutions, network layer, there are positive aspects and negative aspects of such technology. And avoiding the detection, retribution, or reimbursement for unpopular thoughts is possibly could be one of the things. Having freedom of expression, whistleblowing, and all other important ideas can be linked to having access to the anonymous communication technology, but it can be also employed, and there have been already cases that it can be employed for bribery or infringement and other kind of things. What I have observed in several years is that although the negative aspects are there, and as we are becoming more and more residents of the digital world, that need for anonymity is certainly improving and increasing significantly, especially in the blockchain world, as I'm going to talk about in the next slide. And at the same time, the forensic techniques that have been employed to go after any kind of negative aspect, there have remained effective. And all the prominent businesses that started to employ such technologies have got busted and have been the law and enforcement agencies were successful to do that. So the positive aspect that bring is certainly remains valuable in general. And as I mentioned, this is certainly becoming more and more so important as we start to do increase the activities that we have that we perform using the internet. And one of the key things that we are going to observe is the usage of the blockchain technology for performing transactions. And this, which we call a CBDC, the Central Digital Currency Initiative that are propping up all over the world, are going to bring us closer to these technologies where not only now single your bank or single entity is what you communicate with, but your transactions may flow through multiple nodes. And in all such environment, it is essential that that these some of the entities cannot link users' accounts to their to their IP address, so that people could, in principle, figure out who has more money into such accounts and possibly go after them. And there have been already cases where people with a significant number of bitcoins get targeted, where people figure out their IP address and go after them. So as we put more and more of digital transaction online, we will have requirement for anonymity. All right, so that's like my introduction. Here's a very short summary. I could easily spend 1 hour on this one slide itself in terms of how this anonymous communication network has built. Somehow, the anonymous communication networks, thanks to maybe the early thinking from David Chaum, we almost started to work on these at the same time as where we saw the modern cryptography in terms of public key cryptography emerge. And mixing networks is the prominent solution that occurred like 1981 itself. And there have been significant work for sure. As I put in the disclaimer, there are many important works that are missing in this timeline. I was rather trying to put my work in the perspective in this space. And Charm itself also introduced this digital blockchains or digital currencies in the form of blind signatures. And it indeed got picked up from the Bitcoin world later. And I find a lot of synergy in my efforts, which I put for anonymous communication networks and digital currency initiatives of all sort of different kinds. In this talk, I'll be focusing on the topics that I'm showing here in the pink in general, where my aim will be to introduce some of these topics to a small extent to give idea. I certainly see that I may not be able to complete all my topics. So I indeed rely on your guidance in terms of if you see there are enough interesting questions available, I can certainly then make sure to finish my talk in that maybe next few minutes and work towards your questions. So I'll certainly look forward to get your guidance on that. So moving on now, so my at least outline that I'm looking forward to do is I'm going to show one construction to give you an idea how these kind of protocols work. And I'm picking a simplest construction to give you an idea how simple mathematical ideas, interesting mathematical ideas could be employed towards building such solutions. And then I'll look at our effort for the analysis as well as some lower bound things that we work in this particular space. So the construction. I make this word called mixed nets or mixing networks. And that's one of the basic ideas that came in picture, where the idea will be, we'll somehow assume that there are some end users which are simultaneously sending messages of the same size. And what we can assume now is that they all send this message to a series of predefined or sequence of these mixing nodes, which are simply the nodes that are going to take this message, shuffle them locally, permute them randomly, and send them forward to the next node and next node and next node. For sure here, shuffling will be not useful if the packet looks exactly the same on the when it is entering into the mixed net and when it's leaving. So we have to make sure that we employ layered encryption so that packet looks different. But as long as we have access to public key encryption, that can be done. So that cryptography makes sure that we cannot look at the packet and make it out. And this mixing makes sure that then an adversary cannot figure out which message coming from which of the sender on the left-hand side, as long as one of these mixer remains uncompromised. So one that uncompromised mixture will provide me perfect randomization, random permutation, and that is sufficient to mix the nodes entirely. So that's the simple idea, but still has been effective. The key challenge there is to find out all these users simultaneously to be present. But I'll visit that little later. Other idea is that maybe the mixed network inherently requires that message has to go through all these mixes and at least one of them has to be secure. What if we want solution where we do not require any such mixing to be present? And that's where these dining cryptographer networks come in picture. I won't be able to get into the story behind the name dining cryptographer, but I certainly encourage you to search that online. But assume here a simplicity of three nodes or three users, as I'm showing over here. And in this particular scenario, I'm going to assume that they already have tossed a coin, and that coin's outcome is only known to the two parties who are tossing the coin. So as you can see, let's say the first person on the top here is Alice. So Alice and Bob, they have tossed a coin, it come out to be head, and that's the reason the value which is common between them is 1. Inherent assumption there is the Carol over here will not have knowledge about this value being 0 or 1. And similarly, coin toss has done between Bob and Carol and Alice. Okay, and these are the keys that are only known to these two parties. Now the question that we ask that how can we use this coin toss, simple random values that they have agreed with each other, the keys that they agreed with each other to perform anonymous communication. For my initial discussion, I'm going to assume that somehow they have decided at any given round, there will be only one unique sender. And in this particular round, let's say it's going to be Alice. Important thing here is that they have already picked Alice, but they do not know who that Alice is. Only Bob knows that I am not the sender. It could be Alice or Carol. And for Carol, same is the key. And let's say Alice's message is 1. What we are going to do is just use the most simple operation XOR. So what Alice is going to do is she's going to take all her keys, basically the key that she has with Bob and Carol, and XOR that with the message that she wants to send. For others, they are going to again take all their keys, but rather than sending their messages, they are going to just XOR that with 0. And the idea is that we take these messages, these outcome from these local computations, and just post that on any bulletin board or any broadcast channel, any website, whatever mechanism that we want to do. And what we do to obtain the message that has been sent anonymously, take all these three outputs that are sent by these three parties, XOR them, and that will be the output, or that will be the message that is sent by somebody. In this case, that message is 1. If that message has been 0, the output will have come 0, because simply we are just using the very simple property that when you XOR the same thing twice with a particular bit or a bit string, we can extend that to any bit string size here. We are going to basically nullify the both of those strings, and that's the simple idea that is employed here. The key property to see here in this construction is that the message 1 will be present over there. So Bob will know either Carol or Alice send that message, but I don't know who. But I see the message now. And same thing applies to Alice as well as Carol. So that's the key idea over here. But indeed, as you'll see, that, okay, good, but how can they even determine Alice is the person who is supposed to send message over there? And what to do if there is no such synchronization, which looks challenging by itself. It looks like a problem that needs to solve by anonymity itself to be solved first. What if there are multiple messages that need multiple nodes or multiple users that need to send the message? Let's say here we just add the message. If we would have just apply ignoring whatsoever happened and everybody have just taken their message and XOR that, we would have, what we would have obtained as the answer is basically XOR between M1, M2, and M3. And as you can see, I can certainly extend this idea and replace XOR with addition modulo any number in general, right? It's basically a simple operation that we can allow and just keep on adding those numbers over here. And the output here will be M1 plus M2 plus M3. I'm just replacing now XOR with the addition, and I hope you're still with me in that. Okay, so output will be that. That's bad because message is now lost in this process. And what can we do about it? Traditionally, the idea then that was discussed or considered to some extent that what if we run the protocol of multiple rounds and Alice, Bob, and Carol are going to pick the round on which they are going to send message maybe more uniformly random locally. And then hope is that you run such a protocol for n log n rounds, where n is the number of users, and in such a process, then there will be rounds where there are no conflicts, and eventually we will manage to put the messages online. Okay, can we do better is an interesting question, and this is where we come in picture. We look at this system and we see that actually maybe we could use the system in interesting fashion. So now, instead of just sending messages M1, M2, and M3 in my previous example, what if we say that along with that, the we run instance 2 and instance 3, and instance 2, I'm not sending only my message, but a squared form of my message. And instance 3, I'm sending the cubic form of my message. Now, if you have this equation system which is present over here, where if you look at those three instances, the output for instance 1 will be M1 plus M2 plus M3. Instance 2, it will be M1 square plus M2 square plus M3 square. And for third one, as you can see over here. What's interesting for this equation system? It's a full rank system, so we can solve it and obtain messages M1, M2, M3. Okay, but I mean, that's good. But more important thing for us over here is that this is a symmetric across these variables. So essentially, the output that get come from such system, we cannot figure out which one of them was M1, which one of them was M2, and which one of them was M3. Okay, so basically, you can and this is the important property that allows us to make sure that we perform this shuffling that we want, but it's still not possible for anybody who is even solving such system to figure out which of the message belong to which user. Okay, just to give you something that doesn't work, if I replace that with a other full rank system, but which, and we solve that with any of the technique, like just to make everybody clear, Gaussian elimination or anything like that, inherent idea will be we can figure out which of them was M1, which of them was M2, and which of them was M3, and that certainly then doesn't provide any benefit to us, and the loss is prominent. And that's the reason this is one of the equation systems that we find to be useful and helpful there. In fact, as it turns out, this particular equation system is a well-known equation system which are called as Newton power sums, and they can be solved using Newton identities to that we can solve such system for any n in general very efficiently. It's not a challenging problem to solve whatsoever. And that's the some system we employ. So if I have n users, I basically just create n instances simultaneously for n powers and solve such equation system. Inherently, I do not think this is the only way we could solve such a system. However, to the best of my knowledge, this is the only way. But as long as you can make sure that your equation system doesn't reveal the messages, that can be indeed a very nice way to solve it. And if we can solve with the lesser power than what we're doing, I mean, in our case, we have to compute all these significant power. I mean, if I have n players, I have to compute m raised to n, right? So it can be very interesting if we can solve that in a more interesting manner. So if somebody has some thought in that respect, I'm all ears. Please send me an email, and I'll be happy to discuss and understand what you have in mind. All right. So moving on now, I just wanted to give you examples. So the example that I showed could be put in this left-hand side category for dynamic cryptography network structures. But we can take the similar idea and replace that, but where we are pushing this computation now to some servers who are working on behalf of users and perform multi-party computation, secure multi-party computation, if you have heard of this term, to actually get the same effect. And in fact, recently we show how can we do that even when we replace this by MPC by some nodes which only has to be present in the beginning of the system, and then users don't need to still perform all this extensive computation that we are using in the left-hand side to give some idea. Okay, so I'll be now moving to part 2, but shall I just, are there some questions that you wait for, or I should just shoot on?
So there are no questions in the chat, but it might be a good time to just take a moment to see like if anyone has any questions. So if anyone have any questions, please unmute and ask, and then we'll go to the part 2. Okay. So if that is the case, let's actually just complete it and then we'll have some dedicated. I have some questions on my own, but we'll wait it.
Okay. Yeah. All right. Yeah. So yeah, I could not see the chat. Then I thought I'll ask. So continue.
Yes? No. So I guess Devdev has a question.
Yeah. I have a very layman question, really, Aniket. Thanks for your talk, actually. So, like in your mixer network, right? So, that you mentioned at the beginning, right? So, usually, how are those networks or each of those networks implemented? Is it by applying public key kind of things like crypto? Like, how are these individual networks implemented? Like,
yes. So there are, you can expect there are already several ways to do it. But let me tell you the most straightforward way. So as I'm showing in this figure, each of these mixer will have their own public key. Let's say PK1, PK2, PK3. And the idea will be anybody who wants to send a message, they are going to take their message, encrypt that first with the public key for PK3 for the third node. I hope you can see my cursor. And then take that encryption itself and now encrypt that for public key PK2 and take this now bigger encryption and encrypt that for the public key for PK3. And that's a packet that's...
It's like an onion kind of network or something like that?
Yes, like indeed. So, I mean, it's an interesting thing, right? Indeed, it certainly is onion network is one way. I mean, the term that typically employed in mixed network literature is the layered encryption, because onion network or Tor itself is a phenomena itself. In Tor, what happens now that we are on this topic is that they're only going to use public key cryptography to agree on symmetric keys between a user on the left-hand side and each of the node. And they use that repeatedly because symmetric key cryptography is more efficient. So their idea will be all these nodes will have some key in common with the user. They do not know who that user is. That's where the public key cryptography comes in picture. And then instead of using public key encryption, the same layered structure, now we are going to use that with the symmetric key cryptography.
Okay, okay. Thank you, sir.
So just to clarify that, there is a similar architecture that is used in making the TLS efficient. Right? I mean, first establish the symmetric key exchange and then use it to for performance.
Yes, exactly. So same thing is employed. I mean, this is the typical hybrid encryption idea. Use public key cryptography to establish the channel and then continue to use that. In case of Tor, the typical idea is you create a circuit and then use it for half an hour. That's right. But important thing here is that from this unlinkability perspective, all the communication that you perform in that half an hour are linkable to each other.
Right. Right.
So if you can wait for a little longer, it's always better to use public key cryptography for stronger privacy. To go through this now, let me go further faster. Okay, sure. How I go to the next slide? Yeah. Yeah. Okay. Yeah, because okay.
No, this is fast one now.
Okay. Yeah. All right. So now we are moving on to the analysis part. I think turns out when we look at these anonymous communication networks, we had some knowledge about how cryptography works there and what kind of guarantees we required from cryptography. And there have been some work in that space. But when we look at these significantly big networks, how to analyze the properties that they offer was not so well known for significant amount of time. There were some statistical measures available, some entropy-based measures, but not the kind of definition that we are used to, like such as the indistinguishability, differential privacy that we are used to in the other part of the cybersecurity or security literature. So what does it even mean to have anonymity here was kind of a challenge. And that's the one of the things that we started to work maybe around 10 years ago, where the idea is that can we establish indistinguishability kind of a notion that we are used to for the other cryptographic ideas, where the idea will be there will be a challenger and adversary, and there will be two machines, x0 and x1, and the challenger one of them will be selected by the challenger uniformly at random, and then adversary cannot figure out whether it is talking to machine X0 or X1. Okay, that's the simplest form of idea. When the guarantee that we offer here are perfect, so that the probability that adversary cannot figure it out whether it is X0 or X1 are perfect, then we call it perfect indistinguishability. But many times we say that no, adversary may be able to distinguish, but that's only happen with something which is negligible in a security parameter, and that's where the computational indistinguishability comes in picture in such an environment. So the first step that we took towards modeling such scenarios is to first make the scenarios by themselves. And the simplest form that we could look is that we can take any communication and we can put that in three parts: sender of the communication, receiver of the communication, and the message that is getting sent. And then the idea will be we are going to take the real world network and try to model that such that given such series of senders and receivers and messages, we'll run that through such model, and adversary is supposed to sit on some of the nodes on the network, as well as maybe possibly sitting and look at all the links as if it's an AS level adversary. And what kind of leakage goes to adversary, we give it to the adversary and see what all can you figure. So the idea here will be similar to the differential privacy kind of a world. We will have two tables which, let's say, differ in single row, and that will be selected by adversary himself, and he give that to the challenger. Challenger picks one of those, run them through the system, and send all the leakage to the adversary, and adversary is supposed to pick whether it was blue or green in this particular example. And we talk about the adversarial probability here in two parameters. Delta is a standard indistinguishability parameter, and as well as an epsilon, which similar to the differential privacy. And I'll try to give some intuition that why do we see epsilon over here, which is not always the case in many cryptographic settings. Okay. Now here I'm trying to show how typically things should be like, and I'm picking one of the prominent anonymity mechanisms, sender anonymity. Sender anonymity talks about that even when the receiver is compromised, they should not be find out which of the two senders sent the message. So the idea here will be adversary is going to create two tables such that only one row differs them between, and in particular only one sender in that one row differs. Important thing here is that the message remains exactly the same, because otherwise that in itself breaks the anonymity. And that's the reason any anonymous communications that we employ, eventually you still require on top of that something like TLS to make sure that you have end-to-end confidentiality of data. Okay, can be interesting discussion by itself, but just want to make sure that I emphasize on that. And messages are the same, receiver are the same, only sender differs in single row in this particular table as I'm showing. And those are the two things which are sent, and then adversary is supposed to guess which of the two of those tables are employed to generate a communication pattern that adversary is observing. The reason why I see an epsilon which can be non-zero in such environment is that there could be different routing strategies employed in such environment inherently to make sure that there is a good speed. Bob may prefer some nodes because they are in the same jurisdiction, or maybe Bob just likes those nodes or have more trust in those nodes, where Alice may prefer some other nodes because those are the nodes she has more trust on. And if adversary already has such knowledge that Bob typically employs some kind of nodes and Alice typically employs some kind of node, they might be able to not always determine whether it was Alice or Bob, because it's a preference with some probability, but others may still be possible. But they can certainly see that there's a significant chance that mostly if I see a communication in the green part, that it's coming from Bob and not from Alice. Okay, and that's what is getting captured in this epsilon differential privacy kind of thing. But it's important that this not necessarily has to be a distinguishing event, and that's the reason we put that in the epsilon part and not in the delta part. All right, so here is now a typical framework how we look at such system. We'll have a challenger to make sure that we appropriate the adversarial message, and we introduce different kind of a network condition to the environment. we add this alpha adjacency where adversary's input will be taken by this particular function and convert them to something which is more amenable to the challenger, and the protocol is run through this environment. This is this alpha adjacency we add to make sure that the requirement that are set by the definitions are satisfied, as well as we use that as a mechanism to make sure that if we want to weaken the access to the adversary of particular fashion, we manage that through such mechanism. Okay, and the aim is that create such a thing and send that to challenger and run the protocol from there onwards. One of our key applications that we work on is that we take the Tor network that they mentioned. So Tor network was also present on this timeline slide I showed you. It's a prominent network that's employed with similar ideas to provide some kind of a weak anonymity today. They always went for providing communication which is almost as transparent as if you're talking to that website directly, and that's the reason they have weak kind of anonymity, but certainly something which is prominently employed with millions of users every day using that for communication. Some of you might have already have some experience with that system already. And again, the challenge is that people use Tor, but they have not any idea how good or bad the Tor is. What we try to offer is using our mechanism, we build a monitoring system which will look at the Tor path selection strategy in terms of how you pick the nodes in your overlay system, and accordingly, what kind of guarantees that are available to the users in such environment. Again, we were giving more like a bound that our anonymity bound says that, as you can see, it's not at all a good bound, that adversary may be able to do much worse, but this provides an upper bound in terms of the things that adversary can do in this particular environment in general. All right, and then I'll move on to the final part of my discussion, where I want to talk about something we started to work as a canonical aspect from our analysis framework, is to start understanding the lower bound in such environment. And to motivate lower bound, let me start with this simple thing. So as I mentioned, when we look at this Tor kind of a network or the onion routing network, the thing will be there are 7,000 or 8,000 nodes. A user picks 3 nodes out of them to send their communication to the destination that we are sending, and hoping that this communication is remain unobservable to the adversary. Again, we use this layer encryption idea using public key cryptography, symmetric key cryptography. However, somebody might be just following the packet flows over here to figure out that Alice is going to the blue server, because there is no mixing happening in Tor now. It's in Tor environment, every message is taken by itself, and just you remove layer and keep forwarding it, because they don't want to keep waiting for messages from other users. Okay, and but because of that, it do provide efficiency in terms of the latency, because you can look at, let's say, a particular latency for a particular message, let's say 50 milliseconds. Now we are going through the 3 hops, so we are kind of increasing latency by 3 times, so 150 milliseconds or 200 milliseconds based on the processing included. So Tor's aim was to make sure that the latency is low. That's it, then they don't wait for other users' message and whatsoever and continue to do that. But it indeed provides very weak anonymity. On the other hand, Mixnode said that no, we follow a rigid structure. We want to make sure that you send us a threshold number of messages. Let's say they say, I'm only going to mix 1,000 messages. So a user's message come to Mixnode, it is going to sit there unless unless 1,000 other messages arrive. And based on the property, it may just say, hey, I do not have enough message to mix, so it can just tell user back to the, sorry, I cannot send your message anonymously, but to make sure that I provide you privacy, I'm not going to send that message at all. There could be other mixnet design where they, rather than decide this threshold, they say that we follow random delay. Every message stay in the node following some kind of exponential distribution, and hope that other users will also send the message simultaneously so that they can get mixed with each other. So how can we ensure that there are always enough input message available to simultaneously mix is a challenge in mixed network, and we may have to wait longer and have latency because of that. And finally, if you look at dynamic cryptography network, we put other restriction. We say that here on other hand, I have to make sure that all the messages, all the users send their messages simultaneously in every round. If any of these Alice, Bob, and Carol in our example did not send their message, we can not only that we do not have anonymity, it's just that we cannot even reconstruct the message. So indeed, we put here a significant restriction in terms of the number of messages that has to be sent. So I'm taking these three things and I'm putting them in the form of latency versus bandwidth now. So and third axis for me, so you can see in this environment I have three axes. Bandwidth, that means amount of messages, amount of packet that I need to send in such environment. Latency, which talks about time I need to wait. And strong anonymity talks about amount of anonymity I achieve against strong adversary. And for Tor, they say, I want to make sure that I don't add too much bandwidth overhead to the system. I do not want to add too much latency overhead, but the anonymity that they provide is significantly weak and something which is just clear from the bound that we showed in a couple of slides earlier. Mixnet says that I don't want to add too much dummy message maybe, but probably then to make sure that I add I take all the messages from different users and add them, I wait longer. So they say that I go for stronger anonymity, but I'm going to add the latency. Dining cryptographer, on the other hand, says the approach that no, let's add messages from every user and achieve stronger anonymity to such mechanism. So the question that is inherent over here is that can we achieve best of these all three worlds? Like, can we have low bandwidth overhead, low latency overhead, and still achieve strong anonymity? And that's where the final lower bound result comes in picture, that if we take these are the three different axes of strong anonymity, low bandwidth overhead, and low latency overhead, can we achieve all of those things together? If not, what can be good trade-off? Do we understand the trade-off? They're inherent in such environment, and it will be good to know if we just cannot solve this problem by itself. And then maybe given a limit on latency and bandwidth, what is the best anonymity protocol that we can build? Can we now use this lower bound kind of result and start moving them and consider it from the other side to build protocol of my own choice? I don't want to pick higher latency or higher bandwidth. I said, oh, I have this much restriction on my bandwidth. Can I build a protocol which follow this particular kind of a trade-off that is offered by such environment? And this is the kind of a system that we work on and try to provide bound in this particular final part of my talk. So the notion that I'm going to use today is a simple sender anonymity notion, where again, as I mentioned in sender anonymity, we are going to assume that there are two possible senders, Alice and Bob. One of them have sent the message, adversary sitting on the internet as well as at the destination server. And we want to make sure that adversary's advantage to determine whether adversary claiming that the message is coming from Alice and Alice actually sent the message. When you compare that probability with adversary, when it says Alice and actually Bob sent the message, and they are bounded not far from each other by this delta parameter, where this eta is the security parameter for me. And when I say I want strong anonymity, I want to make sure that this delta value is negligible function in my security parameter n, so that even when we compose multiple such instances over the period, that we continue to maintain the anonymity. All right. So the first thing that we have to do here to work towards is that somehow meaningfully define how can we define bandwidth and latency overhead. Because if you look at the network layer, there are just several optimization that we have to deal with. For our analysis, we take more, I'll say, higher level approach. So the idea is where we say we assume that the protocol works in communication round, which are well defined, and that we use that as one unit of time in general. And then we define latency as the basically number of rounds that the message has to stay in the system before it is delivered to the end person. And again, we take the messages and we put them as a unit by itself. And we say bandwidth overhead, we define in terms of the number of noise messages or other messages that we have to add to allow one message to mix. So in this particular example, my latency L is equal to 3, and my bandwidth overhead here is 2 divided by n, where n is the total number of users. In case of if you consider dining cryptography example that we consider, bandwidth overhead will be 1 because each of those n users has to send the message. All right. So to give idea how we build such system, we have to first consider an adversary itself. And because we are working in the lower bound result, we say let's take the simplest or dumbest adversary in some sense. So we consider adversary which is not probabilistic at all. He doesn't try to do any non-deterministic things. Uh, this is the adversary who observes all the links and can try to look at the reachability analysis by looking at the communication that's flowing through all this environment. And to give an interesting idea, let's say we consider two messages from Alice and Bob. They're going to same destination server, and let's say we see that initially do not assume the adversary present on the any node. If the message from Alice follow the path 1, 2, 3, and then to destination, and message from Bob follow the path 4, 5, and then destination, for sure they're apart from each other. And any adversary who can see just the communication pattern on the internet can figure that, oh, the message from Alice, this is the message from Alice, this is the message from Bob. On the other hand, if somehow a Bob message follow the path 4, 2, 3, and then to destination, now there could be opportunity that Alice's and Bob's message can get mixed with each other. Okay. However, if the adversary is sitting on the node 4, again, they can figure out where the message from Bob went, and they say, that message can't be from Bob because I was sitting there and I know where that message went after me. Okay. So just to give idea in terms of the restrictions that are inherent, the challenges that are inherent in terms of building, performing such analysis in general. So what we come up with the first thing is that we define necessary invariant for anonymity in such case. And they could be mathematical expressions that are available in the paper, but I'm putting them here informally. So because we work in round and users are going to send messages in round, we want to make sure that if the message that is received by the destination is received in round R, and if you have put a lower bound, if you have put a bound that a message can only stay in system for L number of rounds, then we want to make sure that Bob, some other user has sent message at least in send at least one message within the time slice of L minus R and R. If Bob did not send such message and we see a message at Eve, we know that the message is actually coming from Alice. But that's not sufficient for war. We also want to make sure that Alice's message and Bob's message should get opportunity to get mixed at some node. And we see that these are indeed necessary invariant. They may not be always sufficient, but they're certainly necessary invariant that we find. And then our aim is to take this necessary invariant and do basically, I'll say, counting in some sense to understand what kind of bound that can emerge from that. And I certainly encourage those who like these kind of analysis to visit our paper to understand how we deal with it. But for timing, I just wanted to then jump to the result that we found. What we observe here that this latency overhead and bandwidth overhead, if you want to achieve strong anonymity, such that the delta is negligible, they follow this inverse relationship where we found the bound that for strong anonymity, you want to make sure that this 2 multiplied with L and beta is greater than 1 in general such environment. The 2 over here we get as a factor from the mathematical analysis that we come. So it certainly is just a constant. It's not an inherent sum to have some more value to it. What we did here as the next thing is to understand now existing protocol where they typically sit in such a system. And we observe that most of the literature typically focus on the one or the other. They either add more messages or try to wait longer. But certainly the space in between where we could possibly build protocols which have a trade-off between bandwidth and latency still need to be explored and has to be considered in general. So Loopix is one of the prominent example which is getting considered. There is already a new company that is working towards building a system based on this. But there is certainly more scope to work across the line to figure out other protocols. When the nodes get compromised on top of that, things certainly you expect to become worse, because those nodes can figure out that who is talking to whom. And that's the reason, if we consider that we have a compromisation ratio of C in general, where C determines the number of compromised nodes that we see in the path, in general, are kind of for this bound that we consider gets shifted. And we also have to consider this compromisation into the analysis. And things indeed become worse for the anonymity in general. So inherently, if you look at this equation on the right-hand side, it kind of indicates that we can't achieve strong anonymity with constant latency, as long as there is compromised number of nodes which are not negligible, or not if we consider more asymptotic, and they are not sublinear in the total number of users or total number of nodes here. So that bound indeed put interesting question that how come then, if you look at dining cryptography kind of protocol that I showed, it just kind of was taking messages and sending them all together and achieving and somehow managing to get the anonymity. So there indeed the bandwidth latency was certainly not non-constant. It was a constant latency in general, and I'll come to that later. If you want to understand the results in general, our results does not only go for the negligible probability, but offer interesting opportunity to understand how these parameters play with each other for non-negligible anonymity, because this latency and bandwidth overhead that we talk about are certainly significant. And I'll encourage you to go to this website and understand. All right, so in short, what we observe over here is that anonymity come at a cost in the form of latency and bandwidth overhead, and they are inherent there. And if adversary can compromise parties, they can indeed increase this cost and towards achieving anonymity. If there are more users who are more regularly sending messages, that indeed help quite a lot from the perfect bandwidth, because then there's no unnecessary dummy or noise message that has to be sent. However, that can only provide some restriction. And then finally, indeed, what we observe is that if you look at dining cryptographer kind of network, because they assume that users have already coordinated and perform those coin toss or agrees on keys, it could be possible to actually find out, using such user coordination, find out bounds which are in between the bounds that are offered by no compromisation of the nodes, and then in between we can find somewhere else a line where we see that user coordination or user employing some kind of a public infrastructure among them to build some kind of a keys with each other and use that to possibly overcome the result. Okay, in this extended Trilemma paper that came up last year, we also went further and we saw that what kind of interesting cryptography primitives may allow to even change these bounds. So we typically, for our analysis, we try to keep it as away from cryptography as possible, and we put them all the cryptographic things in form of the simple assumptions. But using aspects such as fully homomorphic encryption, it could be possible to take things even closer to the green line over here. Or if we try to go for some other interesting kind of a homomorphic secret sharing function, secret sharing ideas, again, could be helpful as. So not only are we look at our results as kind of these are the lower bound, we say that if you want to really break something, these are the interesting direction to consider. So we indeed hope our results can possibly help future developers to pick ideas which may work, because they know here are the ideas which are not going to work. That's what we offer from our analysis. But if you want to work on new interesting protocols, there could be other ideas that could be available. And our hope is that our bounds actually help the protocol developers to just avoid spending time on trying to build the protocols which are not going to succeed. Okay, so indeed, specialized protocols for given specific network traffic is certainly the future direction. Tor came and got used for several years now. it indeed was success story and is a success story. But Tor indeed always aim for weaker anonymity, but making sure the bandwidth and latency overhead are small. But uh, if you want to use, if you want anonymity or metadata privacy at the level of performing transactions on these CBDCs or where we perform monetary transactions through distributed systems or distributed ledgers, privacy requirements are indeed higher. And now is certainly the time where, given the scenario, we build protocols which are tailored for those applications. And there is significant effort that already happening in academia in that direction, and some of them also getting picked in the industry for sure. And prevalence of blockchains and payments over general is certainly going, we are going to see much more usage of these anonymous communication protocols. And it is still very interesting and challenging problem to deal to provide integrity. I mean, we do not touch integrity at all. Anybody can just toggle a single bit on the path, and it could be challenging to even figure out who toggled it. So integrity is a challenge, remains challenge here in such environment. And any node can just stop communication and can create DOS. So DOS attacks in general are continue to remain prominent attacks, and they are certainly even more challenging for the anonymous communication network. And those certainly the topic that we need to deal with. So with that, I'm coming to the end of my talk. If you want to know more about the research I do, I'll encourage you to go to my website and find out our projects as well as on the group website here. Thank you.
Okay. Thanks, Aniket. Let's just thank the speaker once. So just to actually mention, so we are over a little bit over time, but we do have around 10-15 minutes for question answering. So now I think in the audience, if you have any questions, it will be a good time to ask them. You can just unmute yourself and ask the question now. Okay, in the meantime, when the questions are coming, I would, yeah, any questions? So let me actually start at, so what I was wondering, so thanks a lot for the fantastic talk, Aniket. And I really love the Trilemma work. I mean, it also gained some traction, as you are well aware of, right? I mean, it's a very nice formulation and so on. What I was wondering is that two things, I guess. The first one is more technical. That have you? So when you're talking about this usability of this low bandwidth and high throughput communication networks, were you actually thinking about only latency and bandwidth, or are there other factors that you consider or wanted to consider?
So indeed, for several usage, let's say if I'm using this for accessing a website, I can't wait for even 5 seconds, right, or 10 seconds. So there, indeed, it's important to keep latency of the communication small. And I mean, there are already some studies from the usability perspective, and that indeed plays the role. On the other hand, let's say when I'm sending an email or I'm sending a transaction to a blockchain, those kind of applications, or let's say I'm sending a tweet, it could be fine to wait for a few seconds or maybe up to a minute. What we observed by the time when Tor came and now is that our networks have improved significantly. Mm-hmm. So if something was taking in minutes in 2005, it's certainly something that we can manage in few seconds today, if not milliseconds. So given the significant improvements on the network level, in general, I think now is the time where people not for all applications, not for web browsing for sure, but for some applications, they're ready to consider technologies we can offer more stronger guarantees in terms of the anonymity. But for sure, if you consider the aspects regarding web browsing and aspect there, if my web browsing is taking 5 seconds, nobody's going to use my system. And just to add to that, right, I mean, Tor was not the only network that got launched. They were indeed, as you see, Mixnet and Dynamic Cryptography were even older ideas. And there have already been efforts in 2000s to build protocols, and they used to small extent, but they never got caught up because the delays were significant, which is no longer the case.
Okay. Okay. And so on top of that, like systems like Aqua or Herd, which try to actually, on top of this, trying to actually also evade the timing channel, right? Side channel. How do you think these guarantees will change in presence of those systems?
Yes. So if you consider Aqua Herd, those are the two examples, but indeed that literature. So I guess those who follow more system community in SOSP, there have been continuous work from Nikolai Velkovic and several others, where there's Aqua Herd, Stadium, Vuvuzela, Karaoke. So there are different solutions that are getting built, and people have built systems and tested them up to the level of millions of users. So now indeed we have a significant spectrum available towards building our solution. So uh, I'll put it this way: that I mean, I showed that slide with the timeline, and indeed I could not include many of the works over there, but there is a huge interest in academia for sure, and the names that Moina take and think that I read are certainly some of the prominent solutions, which not only build protocols but actually implemented them to and really tested them to see that can we scale subsystems to any significant level. And if you take some of these protocols, indeed we can manage really low latency communications where latency we can keep up to in matter of 10 seconds, something like that.
So even with those systems, like with those improvements of those systems, even after handling the timing side channel, you can achieve those latency numbers.
Yes, absolutely. So whenever I talk about in this talk, whenever I talk about anonymity, I always look for strong anonymity. That's the reason for me Tor is broken, simply for this purpose.
Okay. No, I guess I asked too many. So other questions, the audience? Okay. One last question. I think this is like we are recording this, so feel free to. I mean, this is. But what are your views on private communication versus the safety of like this safety and security conundrum and privacy and safety conundrum? So, do you have any inkling of what the future systems would look like? Because the government wants the citizens to use the private communication until the point when they are not using it for anything secret, anything harmful, and all these things. So, what is the community stand on that? What do you think?
Yes. So this is certainly a question I do get quite a lot, especially whenever I give talk on these topics in India in general. So yes, I'm aware of this. So here's the thing that like with any technology, indeed, if you look at private communication in general, let's say we talk about WhatsApp, where let's say we try to end-to-end encryptions, or here anonymity, all these things possibly do indeed make analyzing communication or any kind of forensic analysis more difficult. But as I included in my slide, we have regularly observed that all such the all sort of forensic techniques using multiple evidence that get gathered have always been successful to go after the user. But the benefit that they bring are tremendous. And I want to actually add not only any technology like these, right? Anything, right? I mean, same thing could be said for cars, right? If we say, or any vehicles, right? If that we only have vehicles which are controlled by government, indeed there could be possibly some reduction in crime because now the motor vehicle available is not available for others to use. Or banking environment, like where do you want private banks or not? So all the technologies, all the things that we can employ could be possibly considered from both angles. As we become more and more digital native, where significant parts of our lives can be figured out, it's more as long as it is becoming more that on the internet, everybody can know that you are a dog. Uh, if people know what I'm talking about in general. So in such an environment, it is indeed the situation that we need solutions so that users can improve their privacy, at least against uh, the players which may go after this information, so private players in general. So I certainly see that going forward, as we see more and more of ourselves and more of us, and as well as each of us putting our information on the internet environment of different kind for financial information as well as our personal information, the need for privacy is just going to increase.
Okay. Okay. So basically, the benefits outweigh the
On the long
risks.
run, benefits are going to outweigh for sure the aspects that are related to otherwise. What I envision maybe 10 years down the line, we'll not even ask this question.
I see. The regulation point would be moot.
Yeah, because I see, again, I'm bringing quite different topic to here, but I want to still add that unless there are drastic change made, the climate change kind of issues can make life quite different for us because it's a slow burning issue and there could be a lot of interesting challenges that we have to do even in the online world. And I find all those things are indeed going to play where privacy could be helpful.
Okay.
Yeah, I know
Fantastic.
it certainly is a bigger discussion to bring that point,
Yeah,
but I thought I still had to mention it.
absolutely. Thanks a lot for the discussion. Any other questions from the audience? Well,
Yeah,
if not, then just let's thank the speaker again. Thanks a lot, Aniket, for joining us in this inaugural talk. It was really a pleasure and an honor to host you. And um, we will put the talk to the audience. We will put this talk. We recorded this and we'll put it in our YouTube link and send it to you.
okay.
So